Welcome to section 15.2, where we're going to continue discussing the evidence for evolution. So we've discussed the idea of what evolution is, but now we want to get into the details of exactly all the pieces of evidence, and we're not going to cover all, but at least a good chunk of the major ones, that support the idea that life has evolved specifically via natural selection. So the first evidence, and the most obvious one, is the fossil record. When we want to look at what the past was like, the easiest way is the fossil record. We can see organisms as they were in the past, and we can also date these organisms so we get a sense of the chronology, the history, the pattern of how things existed, how long they existed, and ultimately what followed the existence of some of these older extinct organisms. So this allows us to piece together exactly what's occurred throughout the history of Earth. So when we look at fossils, one of the things that we find is the fossils that we find in the past bear a striking similarity to most of the fossils we find in modern day. And oftentimes, when we find a prehistoric fossil and a modern fossil, we also find multiple transitional fossils in between. So it's not like we went straight from A to Z. We can oftentimes see A to B to C, etc., until we finally get to Z. And so each step is a relatively small step before we get to what could be a drastic change once you look at something over the course of 100 million or 200 million years. So we can break up these big shifts into many small shifts. Now, an example of this idea is going to be the glyptodont. We find this in North America. It's a really big armadillo-like organism. And not too surprisingly, we find it in the area where in modern day we find armadillos. And so it appears as though at some point the glyptodont was doing pretty good for the environment, but we've already talked about the fact that the environment changes. We have geological changes, we have biotic changes where new organisms move in, some organisms die off, and so you have to respond to that. And you respond to that by changing via natural selection. You know, the individuals that are better now for this new environment ultimately survive better, reproduce better, and it causes a shift. We can see this connection for thousands of different organisms in the fossil record, and that's with a fossil record that's not complete. You know, it'll probably never be complete, but certainly the more we do, the more we find. You know, the more time we have, the more money we put into finding these fossils and processing these fossils, because that's a big part of it. You know, you've got fossils that are sitting in museums that haven't been closely analyzed. So as we go through this, we keep getting a better and bigger picture, and it all dovetails together nicely with this idea of descent with modification. Start with something that's the older version, and then gradually you'll see that most of them change and change and change bit by bit until we get to the more modern version that we see today. Now the next piece of evidence will be anatomy. When we compare the anatomy of different organisms, their physical structures, their internal structures that ultimately compose how they're built, we can look for cues that tell us whether or not some things are related. And what I mean by that is if there's particular characteristics they have that appear to have come from a common ancestor, so that we essentially developed this characteristic a long time ago, and then that more primitive organism, that more ancestral organism, has gradually splintered into different populations that have continued to evolve and change independently of each other, but they still have these remnants, they still have these relics of that ancestral structure that they've just been tweaking. Once again, this idea of descent with modification. It's the same pieces, we're just trying to use them differently because some of these populations are in different environments. So it's more beneficial for them to use it in a different way. And a lot of these new characteristics, where they kind of modify the old one to have a new task, we call derived traits. So ancestral traits are these old homologous ones, these related ones that this ancestor had. But then as they diverge, as time passes and they kind of splinter off as the population itself splinters, we can get new characteristics where we repurpose it. So a great example is the arm. If you look at the arm of pretty much any vertebrate, and even some fishes, you do have the lobe-fin fish that have this same basic structure, you're going to see that there's one bone, what we know as the humerus, that's this upper bone right here. We then have two bones that are going to be the forearm, the humerus and the ulna. We then have a bunch of wrist bones that are small, and you can see this in all of these different guys here, whether it's a whale, bird, dog, or human. And then lastly, we have a bunch of kind of like hand and finger bones. Now, this process is used over and over and over. These structures are homologous. We can see the same pieces in all of these different organisms, even though some of them are using it for a wing, some are using it for a fin or flipper if you want, some of them are using it for what we would probably call a paw, and some of them use it for a traditional hand like we have. So we've done some new things with it, but the pieces themselves are homologous. They're ancestral. We can see that you don't need to have the same pattern of bones. You know, a whale doesn't need this to have a flipper, but we can still see that what they've done is taken an arm and just managed to make it into a flipper, if you will. You know, you don't need to have these exact bones to have a wing, but yet we see that this is what they were working with. This is what they started with, so they modified what they had to make it work, so they got a wing with those same homologous pieces. So homology is going to imply relatedness. It's going to imply connection. It's going to imply they shared a common ancestor that at least had that structure. In this case, a particular pattern of bones in the arm. Now, the tricky part when you're looking at anatomy is there are other structures that are called analogous. Just like an analogy is something that's meant to be similar, but it's not the same thing, it's the same idea with these structures. You know, if we look at organisms that have wings, we would be tempted to say, well, this pterodactyl up here, which is back in the time of the dinosaurs, but not a dinosaur, but it's a flying reptile. We could look at its wing and say, oh yeah, it's got a wing. Awesome. That must be in the same group as these guys here, the bats. You know, they've got wings too. And they probably should be in the same group as the birds who also have wings. So we might think that these characteristics are homologous and try to think that they're connected. But if we look more closely at the internal structure of each of their wings, we can see they've built them differently. You know, when you have the pterosaur, it's a really long pinky finger that makes up much of the wing. When you look at a bat, it's pretty much the hand itself is really elongated to make up the wing, and you can see the fingers are splayed. When you look at a bird, you can see it's once again kind of this whole hand, but in this case it doesn't spread out, it just goes along the edge of the wing. So each of these has a different type of wing. Each of these separately evolved a wing from their own existing parts, but they did so differently, and we can see that when we look at the bone structure. So these are analogous. You know, if you want to fly, you need a wing-like structure. You know, that's just how it's going to work. But there's multiple different ways to get a wing, and so just having a wing does not imply homology. It doesn't mean that you got it from a common ancestor. Indeed, we see that there is no common winged ancestor that all of these guys shared. Instead, what happened is you had some reptiles manage to evolve wings to fly, you had some mammals did this, and you had some of the dinosaurs that ultimately became birds that did this as well. But it's 3 separate times that this occurred. So they're analogous because this is what we call convergent evolution, meaning that this trait is good for the particular environment that they live in, and they all live in similar environments, but they're not actually related. So whenever you're talking about evolution, we'll try to categorize things between homology and analogy, and you just got to make sure you pay attention, because the bones, you'll notice here, are still homologous, still the same bones, but the wing itself is not built the same way, so the wing itself is analogous. Now, to package much of this anatomy stuff and fossil stuff we've been talking about together, we can look at something like whale evolution. When you look at whales, you can see they started off way over here where they were kind of like this little shrew-like guy. And so this was not much to look at, but ultimately over time this guy appeared to start going into this more semi-aquatic lifestyle. And so you can see they started to get bigger and started to get bigger, and you got this sometimes wolf or mammalian, crocodilian looking thing that started to spend more and more time and get better and better adapted to living in the water. And so we see this gradual shift as time passes to where eventually we see the legs start to get smaller. We'll see the nostrils, if you could see up top, you'd start to see these nostrils start to gradually migrate up towards the top where you get like the traditional blowhole that you see today on whales and dolphins, cetaceans would be the fancy term, which allows them to breathe better. But we see this in these transitional fossils happen bit by bit. It doesn't just jump there, it's a gradual transition. Just like if you look at some of these earlier whales like Dorodon still had little rear legs. Now, they wouldn't have been useful for much besides maybe like gripping when you're mating or something because they were pretty small, but it still had rear legs despite the fact it's a whale. It still has a pelvis. It still has all these structures that we think of as being normal, terrestrial mammal structures. even whales today still have some of the leg bones. They just tend to be in their actual abdomen still. They're not fully connected and they don't stick out. And so it still shows us that there's this connectedness anatomically between the whales of today and the whales of yesterday and these organisms that weren't quite necessarily whales. We wouldn't have recognized them as whales, but these organisms that lived a long time ago. There's other structures as well. They've got a particular ear structure that helps them to hear underwater. So there's other modifications we see that we find only in these groups of whale-like fossils and whale-like organisms alive today. So this helps provide us with evidence because we not only predicted we'd find fossils like this before we had them, but now we found them and they've shown exactly the progression that we expect to find and in exactly the time frames that we'd expect to find it. So the last bit for this first podcast, as we kind of wrap up anatomy, is going to be some of these structures that I like to call throwback structures. And I say that because this is when some of these older structures we have, ones that are no longer as useful, so they've kind of faded away, sometimes they pop back up. And so this allows us to see that they are still there, but in many cases they've been inactivated or they've been reduced, but occasional mutations can fire them back up again and poof, there they are, even when we would not expect them. So the first type of structure is going to be vestigial structures. Now these are structures that no longer serve their original purpose. Now most of the time too they have no use, so we might call them useless, or they have a more minor separate use that they've kind of evolved into. But they still are remnants of a structure that used to be useful to an ancestral species. And so we can't just snap our fingers and make them go away. So instead what we see is a gradual reduction as they get less and less and less prominent. So this is a lot like the rear legs on those whales, where they still have some of those leg bones that are, I don't know why I'm pointing up here, but lower, that are still there, but they're no longer connected, they're not very functional. But we do occasionally see a dolphin that does have rear legs. They're not normally particularly useful, but occasionally you see a snake or a dolphin where it's got this leg-like structure that's sticking there and you're like, whoa, why does it have that? That's ultimately this idea of this remnant of a vestigial structure. We just happen to call these vestigial structures that show back up more in force atavisms. So that's where it helps confirm to us that they had these structures. So a vestigial structure in humans would be our tailbone, where all the vertebrae that would be part of our tail that we've lost are fused together and they're basically at the end of our spine. And so we don't really think about this much unless you land really hard on your bum and you snap it and then you're in horrible pain because you broke your tailbone. But we do occasionally see where people are born with vestigial tails, which would be an atavism. So they actually have tails that stick out a bit, which are normally just removed, or else you just have to make sure you date somebody who's into pets. So this is huge evidence to support this idea of evolution, that we came from something that at one point had a tail. Otherwise, we shouldn't essentially have this ability to suddenly have one crop up occasionally. Other examples is you've got many organisms, like this particular guy here, that have lost the ability to see. And so if they're subterranean, you'll see their eyesight can just get worse. That's kind of the first step. But then as time goes on, you can have this particular guy, his eyes have been minimized to the point that they're actually covered by a layer of skin. And so they're still there, but unless you look closely and actually dissect them for the most part, you're not going to even notice they're there. But he's not using them, and so he's not trying to keep them operational. Quite frankly, it's better if they're not trying to operate, it saves them energy. And so over time, we've seen they become vestigial. Now, occasionally one might be born with eyes that function. That would be an atavism that shows us yet again that the genes are still there. They've just been deactivated. But occasionally they get activated, and ta-da, we can see the evidence that they were there a long time ago, and we just managed to turn them off. We see other vestigial characteristics that are not atavisms, like piloerection, goosebumps. This is where organisms that are cold can ultimately use these little muscles to stick up the hair, which helps trap an insulating layer of air, and so it tries to warm you up. Now we've lost much of our hair, so you can see there's not a whole lot there for it to work with, but we still have this trigger when we're cold to try to use this effect to try to get warmer.